Okay, I thought I would do some, let's do some mathematics. Because, I just got some nice comments from my last video saying he appears mental, okay? So, good. Um, you know, say what you like. That's fair enough. And I love the last one was cultist. Sadly, a deranged cultist or something like that. It was quite funny, but it does give me a bit of a chuckle. I'm just a happy Christian. Why shouldn't I be happy? You're the doom and gloom evolutionist, where you've got no existence, no future, hopelessness. Okay, um, you got you should be glum. Why shouldn't I be happy? Why shouldn't I be um, uh, yeah, that'd be about life. Because hey, we've got answers you don't. Okay, let's do some actual maths. Okay, because you're apparently so intelligent, you evolutionists. You guys have obviously thought about the math behind your claims. Okay, so we've got the hope of spontaneous generation. Okay, and the Miller experiment, the famous Miller experiment. Yay, we made amino acids, which was debunked by most scientists. Okay, who said no, it wasn't realistic. It wasn't realistic at all. But let's have a look at actually the mass of it. Random chance of an amino acid. Now, how many amino acid proteins are there um, to make a to make a protein chain? How many um, proteins are there in a simple cell? Simple cell. I say that sarcastically because yeah, there are no simple cells. Okay. So anyway, let's have some maths. Here's some. Hopefully, maybe your mental blindness. Maybe it can be lifted if you actually look rationally at some statistics. Okay, how many proteins are there? There's 20. Sorry, how many? Not proteins. How many amino acids are there? There's 20. 20. So you have for amino acid one a protein of a chain of one, which actually doesn't happen. You need it's a 1 in 20 chance of getting any of the amino acids randomly. Okay, that's pretty easy, isn't it? 1 in 20 for one amino acid. It could be any of the 20. So if we go to 2, that's 20 times 20. Um, and 3, it's 20 times 20. Oh, sorry, yeah. So 3, 20 times 20 times 20, that's 8,000 combinations. Getting up there. Times 20, 160,000. And if we go to 10, that's 20 to the power of 10. Okay, that's 10 zeros. Getting up there, eh? Getting bigger. Okay. Well, what's an average amino acid? Sorry, protein chain. Must be type 2 to 300. Okay, so let's be a little bit. Let's go on the lower side, 150 instead of 200 to 300. So we'll be easy on you. Ha! Not easy on you at all. Anyway, 150 sites of 120 each at each site is 20 to the power of 150. That's easy. Which is 1 times 10 to the power of, what do you think it is? 100? No. 200? Damn close. 195. Okay. So, 1 times 10 to the power of 195. Now that might not seem a big statistic to you. 195 zeros. Anyway, let's carry on. Will that get us a protein? No, that's just if there's 150 of amino acids and there's out of the 20 types, that's just um, um, a chain. That's just the stats of how many combinations there are. Now, how many actual combinations? Actually, of all the protein ones, all the combinations, they don't make actual functional proteins. Okay, all them combinations, you don't get 1 to the not 195 proteins. Not that many. So some Caltech guy did the stats on this, and he said is the actual functional proteins to the combinations ratio is 1 to the 10 1 times 10 to the power of It's 1 in 10 to the power of 74. Okay, now that's a far smaller number, but it's still large. That's for every combination to get out of those random chances. There's going to be 1 to the 10 to the 74th power. Okay, to get a functional sequence of amino acids. Okay, a functional sequence. That's the random chance at this point. But aha, you think it's over, and you think, oh, 1 to the 74th power, yay! It's just like winning lotto or something. No, it gets a little bit worse. Okay, second problem when you're making an amino acid chain, trying to make a proteins out of it. You have the bonding between. Now, naturally, there's a bonding between the amino acids called peptides, and there's the non-peptides. So you need peptide bonds for a protein chain. So that's a 1 in 2 chance, isn't it, for every link? Okay, so we're getting up to like 150 peptides or 149 peptides. Okay, and you're looking at 10 to the power of 45. Now that's adding to the equation. Chance again. It's getting larger. A third problem. Still out there. There's different types of bonds. There's different types you can get called optical isomers, which are like left-handed or right-handed types, and only left-handed are found in proteins. If you get, out of all them chains, if you get a right-handed one, it's not going to fold. Okay, so you've got again 50-50 sort of thing each one, so you've got another 10 to the power 45 added to the equation. So what's our equation? It's getting pretty large. It's 1 to the 10 to the power of 7, out of 10 to the power of 74, but the 10 to the power of 74 plus the 10 to the power of 45 plus the 10 to the power of 45 gives us a chance of finding a functional protein at add the exponents, 1 to the 10 to the power of 164, and you're going to get that's a pretty big random chance. Okay, 1 to the 10 to the 164. Okay, what's that number like? Okay, let's put it in context. The estimated particles in the known universe is something like 10 to the power of 80. Okay, so it's far larger. Or how many seconds have we got all this to happen in? Since so let's go right back to the Big Bang. Okay, so we really give them as much time. So we're talking amino acid forming straight after the singularity occurred. Okay, so for every second, how many seconds have we got for this 1 to the incredible 1 to the 10 to the 164 chance is how many seconds? 10 to the power of 16 seconds. Okay, 10 to the power of 16. How many particles? 10 to the power of 80 in the known universe. And now we've got 1 to the 10 power of 164 of the functional protein being created. Chances. Now how many? Okay, so that's just a functional protein by amino acids. Now how many, and it's a small one, you know, not a bit large one or average one. How many proteins do you reckon you have to have randomly that can do that together before you actually got anything of significance? Because a cell, simple, has the nucleus, isn't it? And it's got all your DNA and your RNA. Which part's going to form first? Is there going to be any, you know, which part? Do you need which part can form first and then wait for the next random mutation of 1 to the 64 for the next protein? And how many proteins is it going to take to make just the cell wall itself? How many How many proteins do you reckon involves in that? Because don't you need a cell wall first around the whole thing to protect it, or are these things just floating around and hopefully are just lasting forever until the next amazing random fluke chance gathering of amino acids forms the next protein, which happens to just happen while this one's still surviving without protection. So which happens first, the cell wall, the membrane, or the innards, the RNA maybe? Does that happen first, or was it the DNA? You know, you guys think it's the RNA, but then hang on, is it just floating by itself? Which part? And that's where, you know, scientists go, oh, this is ridiculous. It's called irreducible complexity. You have a problem, the chicken before the egg problem. You have issues. Okay, so the mass is pretty outrageously silly that the chance answer to, yeah, your amino acid, let alone you're not even close to cell life, not even close, and you haven't got enough seconds in the known in your theory of how long the Big Bang was back, how many seconds there were. You haven't got even enough seconds for even one amino acid chain to form into a protein. Yes, I must be mental. I must be the mental one, not the evolutionist. Yes, you call me names, call me what you like, but look, get a calculator, do some mathematics, and work out who really is mentally incompetent, who really is like mentally challenged and actually believes that sort of thing. Okay, definitely don't think it's me.